Okay. Okay. So, uh, uh, I will begin with this recent work, which make a new connection between optimal transport and optimal design in mechanic. So it's a joint work with Karol Bolbotowski. He's from engineering mechanic, as you can see, and he brings me a new problem of optimal design I didn't know about. And the goal was not optimal transport, but we are bring to, so it's a miracle for me. And in fact, this work is driven by two motivation. So, okay. Uh, so in optimal design, in many problems, you are looking for optimal measure. And in general, it is a stress measure, which is valued in a symmetric tensor, okay, which can be positive or negative, but in my case, in the first model I will describe, it will be the main problem, the pre-stress elastic membrane. We are looking for a vector measure, which is the unknown of the problem, which is valued in a positive symmetric tensor. And there were equivalent problem, but this equivalent is not trivial. We have a non-convex problem, which is called optimal Vaux problem. We are looking for optimal surface on which the structure is located, and he has to resist to drive a load which is vertical, and this surface is set on a planar curve, and you are looking for the best shape, the best distribution of this membrane. And you have also a 3D problem where the stress measure is now valued in 3 by 3 symmetric matrices, and there is a direct relation because in some cases for a given data the solution lives on a surface, and there is a kind of equivalence. It was conjecture, this equivalence with optimal Vaux problem. And besides, when Karol visit me, he comes from mechanic, but he switched to mathematics because he liked very much geometric measure theory. And he had to face a problem where you don't know a priori the dimension of the optimal structure. And in mechanics, they like one-dimensional bar, so set of bars. It is called truss structure. You can have surface. If you know R3, you don't know a priori. So you have to find, as the sigma is unknown, you have to apply the theory of plate of beams simultaneously, because you don't know what is the dimension of the optimal structure. And it is why he came to visit me and in Toulon. And we discovered this connection with optimal transport. But the new thing, not really new, is that the metric is not given a priori. It comes from the problem itself. Okay? If you want to see better the connection with mechanics, I give this reference, which is a very nice paper by Karol. And all what I will discuss now is in the paper, including a conjecture, which appeared recently in ARMA. Okay. So the plan of my talk, I will recall the old problem of classical compliance, where we use the Euclidean metric. It is the work we did with Giuseppe at the first meeting in optimal transport. Then I will describe the new setting, okay, where we had some constraint on the measure, and then I will discuss a duality approach in the smooth case, because there is a real problem of achievement of the dual problem. And then, in order to relax this duality framework, which is not completely achieved because there is no existence, we use a new approach via maximal monotone map, and we are optimizing among maximal monotone maps in order to find the good metric of the problem. And then I will consider show numeric, which has not base optimal transport, but on a two-point scheme. Okay. Then, I begin with the classical problem. I consider a priori a convex. It is not necessary, but to have the Euclidean distance, it is necessary. You will consider the geodesic distance in omega, which is supposed to be convex. I take a scalar measure, so it is a scalar problem, where the load, if you speak of mechanics, it is a scalar measure. And the unknown is a conductivity coefficient. And you make the constraint that the integral of A is smaller than a given parameter, M. Okay. So if you have a distribution of one material, that means that the proportion of material is given. Okay. So the problem I will discuss is not completely equivalent to the one where you mix void with a material, but by relaxation you end up in the scalar case with the same problem. Okay, and so you given A, you solve the diffusion equation with coefficient A, with, for instance, a Dirichlet condition of the boundary. And it is like optimal control problem. Okay, the control is A. You solve the equation, and the target is what is called the compliance. Okay, which is a convex function of A. Okay, so you have a convex problem. So a priori, but in fact, the sequence of minimizing sequence can oscillate and also concentrate. And in many cases, they concentrate in lower dimensional subsets. Okay, line major or surface major if you are in L3. Okay, and if A and U are smooth, it is well known that you have optimality condition which consists on solving econal equation on the set where the structure has a density, strictly positive density. Otherwise, with the same constant, U has to be Lipschitz with a constant equal to, and after you tune the constant in order to fulfill the mass condition. Okay, so the existence issue is not, as I said, you have no a priori bound on AN except in L1 bound because of the constraint, the mass constraint. And in case of a discrete load, F doesn't belong to the dual of small F space, and there is a problem of existence. So the compliance might be infinite if you want to include any A. So there is a problem of definition of the compliance. So the first job is to extend the definition of the compliance, taking instead of a density A, any major which is non-negative on omega, and the compliance it is not really a control problem, because in that case the target, the goal is to minimize this convex functional of mu, which is given by the supplemum. So it is a dual formulation which fits very, very well to the problem, because here you don't need any regularity on V. You can always integrate the gradient of a smooth function respect to mu. After comes a step which is important, is a relaxation of this, because if mu is a line, you cannot give a sense to this integral. So you need tangential calculus with respect to a major mu. So it's an old story. And it goes back to 95. We work very much on this problem of extending equation using a kind of projected gradient. So in mu almost every point you can define the tangent space, and you project the gradient, and this projective gradient is a closable operator with respect to the L2 mu topology. And you have a good setting for the problem. And you can easily rewrite the optimality condition in this form. So you have the equilibrium, minus divergence of the flux major is equal to F, and the constitutive law links to the potential U, which is solution of some of the initial problem, but it is also a solution of a dual problem, as we will see. It is given by the gradient of U times mu. Okay, and you have the econal equation and the same Lipschitz condition, which is independent of the major in some sense. I put almost everywhere, but U has to be C Lipschitz. Okay. More interesting is the link with optimal transport, because using this you can build explicit solution without doing numeric. And sometimes numeric doesn't give the good shape when it is not smooth. And so it is what we discovered a long time ago, 97, with Giuseppe and Pierre Sepécher. Of course, it goes to the dual problem where you maximize a linear form with respect to U with a gradient constraint. And as well known in Rubinstein-Kantorovich theory, it is linked to the W1 distance, which I recall here. Okay. In which the distance is here the Euclidean norm. So why the Euclidean norm in this problem? Because you have a Lipschitz constraint with respect to the Euclidean distance. Okay. If omega is not convex, it is a geodesic distance with respect to omega. Okay. And the problem is the Dirichlet zone. The Dirichlet zone is something where the transport is free. So you can add also the boundary in this framework. Okay. So this recall has been done. So I don't take unbalanced transport, as you see. We put plus infinity, the major have not the same. Okay.
At the bottom there, C equals 1. The constraint on grad U has to be 1.
Yeah, it will be 1 or some constant. You tune it so that you feel the total mass constraint. Okay. But you can easily rescale everything.
Then the constant has to appear on the
Sorry. Yeah. Oh, I should. Okay. So the dual problem in terms of convex analysis is given by the supremum of FU. Where, for instance, U has a Lipschitz norm equal to 1, constant equal to 1. And I consider the distance of, it is important, I take a F which is positive, otherwise it doesn't work so much. There is other formula. And you consider the distance of F to the boundary, which is the minimum of W1 Fg, where G has the same mass of F, but it's concentrated on the boundary. Okay? So you have a hidden source of the boundary. As usually, we have a Dirichlet condition. There is a Neumann equivalent condition. We give the good... okay? And we establish this equality, which is very simple. That means that this first equality between the supremum and the infimum defining W1, it comes from Kantorovich Rubinstein, okay, and this is the usual dual problem which correspond to this problem here. And you dualize this, you minimize the total variation of a vector major whose divergence is equal to F in sense of distribution on omega. Okay, and by making, so you have the compliant is a supremum, you have an infimum supremum, you can switch infimum and supremum, and you establish very easily this equality. Okay, so there is a direct connection between the problem with a prescribed mass m. Okay, m appears at the denominator because if the the weight of the structure is goes to zero, you cannot resist to a load. So the compliance goes to blow up to infinity. And when F is a sign major, you have equivalent formula. You have to add the good quantity to the positive part or negative part of F. There is no problem to do that and to prove that it is a minimum. Okay. Now, interestingly, you have the recipe to guess what is the optimal Q. So the sigma here, you are in a scalar case. The Q is a vector major. There is no matrices here. And in that case, if F is positive, the solution of econal equation with a constant 1 is the distance to the boundary. It is also a viscosity solution of gradient U equal 1. And to build the optimal plane corresponding to W1 of F to J, you simply consider the projection at any point in omega on the boundary. So it may consist to one point or several points. Several points is important for the following. Okay, at each point you associate the set of projection of X on the boundary. Okay, and then you are looking for a plane gamma which takes this form. So F is the first marginal, okay, and the second marginal is on the boundary, because here you integrate on the boundary, okay, and you have to find in this decomposition what is the optimality condition for Px. So for any x in omega, you have a probability, but which has to the support. The only condition you have to meet is that the support Px is supported by the projection point of x on the boundary. Okay. So for any choice of Px satisfying this, you build the optimal measure, which is the superposition of a straight line. So you transport in a straight way with respect to this is a geodesic for the Euclidean matrix. You superpose this array, and you have the optimal flux according to this decomposition. So, okay. There are a very nice example. I give you a very simple example because this trivial example will be very surprising when I add some constraint to the problem. So I just take a Dirac mass in a square, okay? In that case, the projection point is reduced to only one point. So the probability is a Dirac mass. There is only one possible optimal transport map, okay? You obtain the optimal measure, which is carried by the segment here, and the optimal flux, which is in the opposite direction, okay, which is the gradient u. U is the distance, so you take the gradient projected on the tangent space, which is the horizontal line. In that case, you have a uniqueness. Now, if you move horizontally x naught to the diagonal, you will have two projections. In that case, you have infinitely many solutions, which are combination of one-dimensional measure on vertical and horizontal lines. And if you move the point to the center, you have 4 points. So you have a space of the subspace of dimension 4 for solution. Okay. It will be very important for the cycle. So I come to the. It is generated by 4 solutions, convex combination. No, not subspace. Sorry. So I consider now. So to explain the optimal membrane, I first make a substitution. Instead of taking a scalar measure, I replace the measure mu by a tensor measure, which is positive. And the mass will be the trace of this measure. Okay? And how this tensor measure comes in is that you have a diffusion equation which is anisotrope a priori, and the energy with respect to a test function V is given by sigma gradient V. I can write this as a scalar product. So I define, instead of the compliance of mu, the compliance of a positive tensor sigma. And this problem is well posed. Sigma is positive definite. Positive. Okay? And if you take the identity times mu, you recover the previous problem. Okay? Because I normalize the trace. Huh? Okay? So if you take sigma equal mu times the identity in dimension d, you obtain integral of mu equal m. So it is the extension of the set of admissible measure. In the sense you have now tensor valued measure. But the problem are very much linked because you can show that when you optimize sigma with a constraint, you have a rank 1 tensor solution. So it is more or less the same. Well, in case of elasticity, it's more complicated because you have all the four tensor. There is a paper by Levinsky, Bolbotowski, Karol graduate with Thomas Levinsky and Rybka for PhD. He is from mechanics. Okay, so what is the pre-stress membrane? So there are three models which are equivalent. I described the first one only. You have the pre-stress membrane problem. So the design, as I said before, is now a tensor valued function where the sigma has to be positive. Okay, it corresponds to the stress, the pre-stress in the membrane. So you take a membrane, you stretch it so that it resists to a vertical load. Okay, so you create a tensor sigma. Okay, and it is the job of designer. It is very easy to make this, except that the divergence of sigma has to be 0 inside. Okay, if you reinforce ceiling voile, you always okay, I will come back to that later on. So you have a vertical pressure, and the U represents the deflection of the membrane, which is pinned vertically on the boundary of omega. Okay, so you have a planar membrane, so it is a 2D problem, but it at the end, but originally it is a 3D. Okay, so when you pre-stress a membrane, you stretch it on the boundary, so you have the divergence-free condition. It is the equilibrium, the elastic equilibrium of a membrane, planar membrane. Okay, but I consider the vertical displacement of this membrane subject to a vertical load. Okay, so the sigma has to be in tension only. Okay. In the vote problem is the contrary. It is in compressive regime. So you have to choose, but you have a sign. And you minimize the compliance with this divergence-free condition. It doesn't work? Okay, divergence-free condition. And instead of putting the mass constraint, I add a Lagrange multiplier. In fact, the problem are equivalent because you have easy rescaling. I show it here. If you can solve the problem, you can solve for every total mass m given. So you have two infimum. This is the infimum without the constraint divergence equals 0. I call it Z. While the pre-stress membrane Z naught correspond to the same problem where you add the divergence-free constraint. Okay. Of course, there is an inequality. And I want to point out that the divergence-free condition is very stringent because for instance, if you take a scalar tensor, identity times mu, the divergence condition implies that mu is a constant density, which is not very interesting. You have but it is a pre-stress membrane with a constant P density. So you have not very much choice. Now, if you take, you have interest, in fact, to take a curve if you are in R2. If you take a curve, there is a curve C, smooth curve, okay? Automatically, if sigma is carried by this curve, automatically sigma has to be in the direction of tau, tensorial tau, where tau is a unit tangent vector. And you can put a density P here in front of this tensor, but the divergence free condition implies that P is constant, as here, okay? But in addition, when you compute the divergence of this, you obtain the curvature of C. So automatically, the curve has to be a straight line, and this straight line has to connect the boundary point of omega. Okay, so you can use a straight line, but you can use also a combination of straight lines crossing with a good angle. Okay, and you can represent what I call truss measure as superposition of elementary stress measure which are carried by segment. So this is the formula here. Okay, you can take convex combination of such stress, and in that case, the divergence-free condition correspond to this equality holding for any test function. Okay, so it is like a transport, but you have a constraint. Okay, the gamma couples the endpoints of the bar. Okay. Now there is an equivalence theorem, which is very simple, which says that the FMD problem and the divergence free problem are equivalent if only if F is supported on the high ridge of omega, that is the set of a point in omega whose distance is maximal to the boundary. Okay, it is called high ridge. Okay, and to see this using the decomposition of the transport map, which is here, and the condition that the probability has to be supported by the set of projection, you find that the divergence condition is equivalent to say that the barycenter of each probability nu x is x itself. So x has to be, in every point in the support of F, you have to be in the convex hull of the projection point. And it is equivalent to the fact that you belong to the set M omega, which is here. So if I come back to the square, here you have only one projection, so it is not the barycenter of this point. So you are not the only point in the high ridge is the center of the square. Okay, so we did a numeric with Carol because he has a good problem, and we had this structure for to get free boundary divergence free condition. You have a structure with a different weight on the lines, of course, and here you obtain exactly the middle point of the side of the square. We were very, very surprised by this. And so the question, here you have a transport, you're using the Euclidean metric. Maybe there is an unknown metric for which you have 4 geodesics to the boundary. Okay.
So the x naught is not on the diagonal, it's below the diagonal.
Yeah, here is not really on the diagonal. No. But after we have an explicit solution of everything in this case. Okay. And so if I consider admissible sigma, the sigma which is given by without for the optimal design problem without the constraint is not admissible, as I said. Now you can make the continuation of this bar up to the boundary, but this one is not optimal. Okay. Okay, and numerically we play with that. We take 3 points. Here you take a line and a point, so you have a structure which look one-dimensional in some sense. So one of the questions is to know if in general you have, like in Mitchell problem, a superposition of bar, which is not completely true. And here, when you have 4 points, you have several solutions depending on the algorithm. In fact, what we will see that here you have a very flat metric, so you can do what you want, and you have all these geodesics, okay? But you need this to make the divergence-free condition. Okay, so I use a very classical framework first. So it is what I call the PDA approach, okay? So you have to minimize the convex function of sigma, but the divergence-free condition is handled through the duality. So I can characterize the divergence-free function as this function such that the integral of sigma times the symmetry, you can take the gradient of W, or the symmetric gradient is the same because sigma is symmetric. So if sigma is divergence-free, the integral of sigma symmetric gradient of W integrated with respect to a measure against a smooth function is 0. Okay, and it is true for any W. I can put together the equilibrium constraint divergence Q equal F. So you have a PE. Unknown PE is the flux Q, which is a measure, and sigma, which is a tensor valued measure. And the admissibility of this PE, you have the boundary condition for U, of course. W, the divergence-free condition is only on the interior of omega. So W by duality, W is a 0 on the boundary. Okay, so you have this relation, and now you have a primal problem, which is not completely obvious because here you have a convex functional with respect to Q and sigma. In fact, it turns out it is a convex one homogeneous functional on measure. Sigma is positive, of course the definition is clear. Otherwise, if Q doesn't belong to the image of sigma, you put plus infinity. And if there is several pre-image, the scalar product doesn't depend on the choice. So it's just a notation. And so you minimize the convex function on measure with divergence-free condition. Okay, this convex function is one homogeneous. This is one homogeneous integrand, which is the support function of the convex subset. This convex subset is given here. Okay, and the dual problem. So before it was the supremum of FU with gradient U smaller than 1. Here, instead of gradient U smaller than 1, you put, if you take the trace of this, and if W equals 0, you recover exactly up to factor 2. Well, factor 2 is because of Carol. He wanted to put 1/2, and we will always have square root of 2. Well, okay. And this tensor here appears in von Karman theory of plates, in fact. So it is linked also to a nonlinear model of plate. And so you have a similar problem, but here you have not equilipsis function because you have E of the W. Okay, and so the compactness of a maximizing sequence is not clear. What we could prove is that the maximizing sequence are bounded in W12 and in Holder space was C1/2. Okay, and we could prove only that W is bounded in BV. So a priori, you cannot expect to have a solution which is continuous for the W. Okay. So we did the duality. There is no duality gap. Okay. And when you have to detect if Q sigma is optimal and PE UW for the dual problem is optimal, you have to test this extremality condition. Okay. So just if I consider admissible Q sigma which has finite energy with respect to the functional convex functional, automatically sigma has to be Q has to be absolutely continuous with respect to sigma, but sigma is carried by the trace of mu, so I put Q equal something times mu, but the density has to be in the image of S, okay, where S is the density of sigma with respect to its trace, okay. So doing this, you have a system of optimality condition, which looks like the one I discussed before, but there is an additional variable which is here. The econal equation becomes that. Okay. The Lipschitz constraint is replaced by this in terms of measure. Okay. And you have equilibrium condition. Okay. So it is valid only. So I take the tangential gradient. And I have to assume that U and W are Lipschitz. So it's a problem of regularity we could not solve. Okay. And but doing this, we find explicit solution. For instance, if omega is a disk and F is a Dirac mass inside, you have explicit solution which was found by Carroll, because when you consider the Vaux problem, you have a circle, you push vertically. What you do, you consider a cone, which is a function I draw here, okay, and it will be solution of the dual problem, and miraculous is that the W is proportional to this function with a constant direction, okay. Doing this, we find explicit solution. In which also we can put the Dirichlet condition only on the part of the boundary, in fact. You can build the solution taking any probability measure on the boundary, okay, and you consider this flux and this sigma and this PE UW. It is optimal, whatever is a major nu. So that X0 is a Barre center.
It's not letting me share slides.
And doing
for
this,
some
you can
reason.
solve the problem on a rectangle or a square
preferences.
By using this construction on a circle and making the good continuation of UW by 0 outside the circle. But what you mean that you need that X0 is a barycenter of some projection points. So it depends on the location of X0 in the rectangle. Here there are 2 points. Here you have a solution using 3 points. Okay, you have a triangle. And here you have a solution using only 2 points. Okay. In all cases, you can solve the problem. Okay. No. Voilà. So I will have to pass to the optimal transport problem. Sorry. So there is no existence a priori for the dual problem, but this constraint is equivalent to a 2-point condition, which is set here. Okay. So you have this regularity at least. Okay. And in fact, the job is to replace this, to relax this. And if you consider this change of variable, you take the identity minus the W of X, you obtain that V has to be monotone because of this, because you obtain V of X minus V of Y, X minus Y is greater than U of X minus Y squared, so it is positive. but it is maximal monotone whenever V is smooth, and V is coincides with the identity outside of omega, which is important. And if you have compactness for this maximal monotone map in the sense of Koratowski, you have a compact class. Okay, so you can minimize with respect to maximize with respect to this, and so you obtain an optimal maximal monotone map. And then what you do, you construct a metric associated to V. Okay, and you will consider optimal transfer with respect to this metric. Okay. In fact, there are two strategies. It is a geometrical approach, or you can use directly the two-point duality scheme. But in that case, you have a truss-like structure. And again, you have a problem of existence in that case. Okay, so you have a maximal monotone map, and the constraint becomes u of x minus u of y smaller than some pseudo distance. It is not a distance which is given by this. Okay, but it is not subadditive, this, but you can prove that it is like a length space. That means from this kind of distance you build a real distance, which is obtained by taking the infimum. You take a chain polygonal curve between 2 points A and B, and you optimize the sum of lengths, and you obtain a semi-metric, okay, which is more or less associated to the symmetric tensor, which is when V is smooth, it is symmetric gradient, okay, and you apply Rubinstein duality, okay. So you have a lot of properties. Sorry if I have no time. So you have the Monge distance with respect to this metric which depend on V. Okay. So the same scheme, and what you prove that the supremum of dual problem is the same as maximizing the Monge distance between F and the boundary of omega, when V belongs to this class of maximal monotone map, and you have existence of optimal maximal monotone map. Okay. Okay. I pass this. I just show you the numeric. You have a duality scheme, 2-point duality scheme. So it is like a conical. It is not linear programming. It is a conical programming. Okay. But there is there is a conjecture. Is that the 2-point scheme gives the good there is existence for this when the load is finitely supported. It is linked to extension conjecture, which is independent of interest. You can find in the paper if you're interested. It is independent interest, and then you have numerical oscillation using a mosaic toolbox, and also we compare to finite element method. Okay. So here you have in red the optimal sigma, in blue the optimal flux with the direction, and here the optimal u. Okay. Okay, 5 points. Here it seems the solution seems to be unique. Okay. Here you have uniform pressure, which is very nice picture. And here we play this game using the solution of this. You have the good metric V, and you compute the geodesic from x0 to the boundary with respect to the optimal metric, and you obtain 8 geodesics with curves here. Okay, numerically, it's not. And with the finite element method, you have this, which looks like self-similar. We don't know why. It's mysterious. Okay, so you have a diverse example of load, and here you have an example where the Dirichlet condition is set only on 8 points, and you have this very non-smooth function W, which seems discontinuous in that case. Okay, sorry for the.
Thank you very much. So maybe if we have time for one question, maybe. Yeah.
Yeah? No, no, no. No, no, no. No, no, it's just a situation when there is no constraint on sigma. It is very easy. The proof is very easy.
All right, so let's thank the speaker once more, and we'll set up for the next talk.
The most important part of my talk will be on the board, okay?
So our next speaker is Mathias Beiglböck from Vienna. He's going to tell us about the Wasserstein space of filtered processes.
Okay. Yeah, as I said, I will ask you to pay specific attention to this board here, okay? So the whole talk is about something which I think is a very basic phenomenon, but it's I think actually important or quite important in some areas. So this is about how one should measure the distance between stochastic processes. So it's a bit of a philosophical question. When do we think that stochastic processes are close to each other, and when do we think processes are far away from each other? And for this, I draw two processes, each with just two time steps. So this is my time axis. Maybe this is my process xt, and it corresponds to a probability measure p. Then we have another process yt, which is also in finite discrete time, and which is represented by a probability measure q. And the first process is just constant in the beginning, and then it goes up or down to the level of plus or minus 1, each with 50% probability. So that's my first process. The second process starts in either plus epsilon or minus epsilon. And then again, it goes up or down, each with probability 50%. Okay? And I mean, of course, if we represent them as probabilities, then I mean, there is each just 2 points. So this is just two probability measures on the plane. I'm just drawing them in a slightly unfamiliar way. Okay? And I mean, the question, which is really the basis for the whole talk, is, do we think that the measures P and Q are close to each other or not? Yeah, so classically, we could calculate the Wasserstein distance between those two measures. And this is a check whether you are following what I'm trying to draw here. What is the Wasserstein distance of P and Q approximately? Yeah, so let's say it's roughly epsilon, okay? And in this sense, these processes should be close to each other. The point I want to make is that if you do anything like stochastic control, if you use this as a model for something in finance, then there is something strange happening. And the reason is, if you think that these are, I don't know, some outcomes of a game in a casino, and you're allowed to bet at time 0, then with this process, betting makes no sense, because if you are allowed to bet at time 1, then chances of going up or going down are equally likely, and of course there is nothing to be gained. So this is a martingale. On the other hand, if you're in this process, if you know you're at plus epsilon, you know for sure that the process is going to go up, and so you would start to bet on this process. Okay. So the point is, whatever type of stochastic control problem you put here, this guy is taking away information in the beginning, and this makes a huge difference. And this cannot be seen by anything which metrizes a weak topology. So the question is really, what's a better way of measuring distances when you think about stochastic processes, or what's a way to upgrade Wasserstein distance? So we want to look at what I call an adapted notion of Wasserstein distance. I will discuss how this can give you stability results. I will discuss how other communities have been trying to solve such issues. And we will talk about how these things connect, and finally we will talk about what would happen in continuous time. Briefly, Wasserstein distance, if we assume that P and Q are continuous probabilities, then we can use such a Monge formulation. And also let me say at this point that for the whole talk I will talk only about P equal 1, but it wouldn't make a difference to have a general P, it's just to avoid P, okay? Okay, we have this Wasserstein distance, we have the usual Wasserstein distance. For stochastic processes it would mean at every time point I look at the whole path of my stochastic process, and I use the whole path of the stochastic process, I use the whole path here to determine what the y outcome is going to be. Okay, so in this picture I would use the information about the whole path in order to map here with T1. And in a way, I think this is what's causing problems with classical Wasserstein distance. That even if you're trying just to determine the target point here, you're looking into the future and you're using the whole information about the future path of your process. So what you want to look at maybe is an adapted version of this Wasserstein distance, where if you calculate the first coordinate of your mapping, you're allowed to use only the first coordinate of the X process. Guillaume, you look very... Oh, that's great. Yeah, that's a wonderful association to this, yeah. So, okay, adapted Wasserstein distance would mean we ask this condition on T1 and T2. So this would be a Monge formulation, which works fine if you have continuous measures. In general, you would write this adaptedness as a condition on couplings. And I mean, as I said, okay, so this definition of couplings, this says about something is not supposed to depend in some way on the future. But you can also think that the set of pi-adapted couplings is really just a closure of what you get from these adapted Monge maps. And then, of course, here a great question would be, what are examples of such pi-adapted couplings? So the first example is a product measure, and the second and much more interesting example would be Knote-Rosenblatt coupling. Knote-Rosenblatt coupling is like the prime example of a canonical adapted coupling you would look at. Okay, so the main focus of my talk is to study properties of such adapted Wasserstein distances. So really just adapt this Wasserstein distance, but without looking into the future, if you think there is a future. On the positive side, what you get is many stability results which are not true for usual Wasserstein distance. Yeah, so things you do in optimal stopping, in optimal control, in many things you do in finance, there is no continuity with respect to weak topologies or Wasserstein distances, and you have Lipschitz continuity if you impose this adaptedness condition. Another example is so in weak optimal transport. Okay, this was introduced some years ago, and I think the early proofs of existence of optimizers, duality, cyclical monotonicity, they are a bit involved and they need quite some conditions. And something interesting which is happening here is what all of these things are going away if so you get proofs which are just the classical proofs if you use adapted Wasserstein distance in the background. And maybe a third example which I have put here is this concerns hedging in mathematical finance, and I guess I'm starting to be much too quick because I want to save time, but in any case I'm only quick on the finance part. Okay, we can ignore it in any case. Yeah. In finance, you're always interested in some replications. So you assume you can replicate, you can write something, you can write some interesting financial object as a stochastic integral with under a certain model. And the question which has been ignored for like 40 years there is if your model is not completely correct, does this equation mean anything in a slightly different model? And the reason is that you have no continuity with respect to usual weak topology. If you put adapted Wasserstein distance, then nicely you get you can control, say, the L1 error of such hedging in terms of adapted Wasserstein distance. And the reason I put this is that such inequalities are actually sharp if you look at the most basic setting. Yeah, so in my opinion, what this underlines is that if you want to look at such stability questions, adapted Wasserstein distance is not only solving a topological problem, but it's also at the right order of magnitude. So it's capturing things at the right order. Okay, I should emphasize that this phenomenon, of course, we are not the first ones to see that there is such an issue, but in fact there is many different people from many communities which recognize that sometimes you want to do something which is different from weak topology, that you want to look at some proper extensions of weak topology. So the first to do this is David Elders. What David Elders was doing is, instead of looking at probability measures, he identifies probability measures which with a more complicated object. So this is a prediction process, and I mean, so this is the type of slide which is not meant to be read. It's just meant to say that this is somehow complicated. Yeah. So I think if you have not seen the prediction process, there is no chance you can understand it from my explanation here. But the point is, okay, Elders takes a stochastic process, makes something much more complicated out of the stochastic process, and then he pulls it back. And this is what gives David Elders he called it extended weak topology. And then there is German economist Martin Hellwig, and he is in a way doing something similar. Again, he is taking his process and he is making more complicated processes out of it, is pulling back a topology. And again, he gets an extension of a weak topology. Rémi Lassalle, he calls this causal transport. He's doing something similar to what we have seen before. He's just symmetrizing on a different level. Yeah. Then there is actually several different people or different communities who recognize that maybe you want to do an adapted Wasserstein distance by forbidding T to look into the future. So this adapted Wasserstein distance was discovered several times under different names. Okay, and then there is yet another approach which you might take, namely weak topology tests against continuous functions and to look at convergence, and instead you could test against easy stochastic control problem and try to make them continuous. Yeah, so this is another way which by construction enforces that you have continuity of such problems. Okay, so there is many different approaches to deal with this, and interestingly, I mean, these people really come from different communities. Many of them date back to times where there is no proper internet, and so it's, I think, easy to see that how they are not looking at each other's papers. Okay, but it turns out in the end, all of them end up with the same topology. So if you put all of them on the context of probability measures on Rn, then what you get in all these instances is actually the same extension of the weak topology. So I think that's first of all, it's nice because it gives you the feeling that there is something canonical going on. And a second thing which is nice about this theorem is that it's actually very useful. The reason that it's useful is this different. So with this, if you work with this metric, it turns out it's a very strong metric. If you have this as an assumption, it's very easy to prove things with it, stability from it. It's actually very hard to show that simple processes are dense if you look at this adapted Wasserstein distance. And somehow, for instance, the Hellwig metric, this feels much softer in a way. So if you want to prove that something is dense, or if you want to have something about finite approximation, then you want to work with Hellwig. That's actually the reason we came up with this theorem. We wanted to show that finitely supported measure, so dense with respect to this distance, and we couldn't do it, and we could do it for Helvig, and then we thought what's actually the connection. Yeah.
When you're talking about all adaptive topologies, you mean all in this list?
All in this list, yeah. Okay. There are other ones, yeah. But okay, so I was joking that these people don't know each other's papers, yeah, and then we are there and we finally read all the papers, okay. But then after we started working on this, so after we published this, we found out that there is actually more adapted topologies, which we had also missed. But maybe this could be your favorite topology, yeah. Measure the distance by just looking at the distance which comes from imposing Knote-Rosenblatt. Yeah. Okay, but nicely, still all topologies are the same. Yeah. So the result stays the same. Yeah. Okay, so I like. So I think it's a nice fact. What's not so nice about this theorem is that the proof is really a disaster. Yeah. So I think I never fully understood the whole paper at one time point, because it's so many things of working around with nested and nested and nested conditional expectations and trying to fit them together, and analysis is also not trivial. So I thought it's a useful result, but I don't understand why it's true. And maybe worse, what you really want to do is you want to have this theorem in continuous time. So for processes in continuous time, and I thought, I guess it's true there, but we will never prove it, yeah? Okay, luckily there is Gudmund Pamar has found a new approach, and I think later on I can maybe say some words about what's his idea of why these topologies are actually the same is, yeah. Okay, so it's nice that all of these topologies are the same, but there is something about these topologies which doesn't seem so nice, and this is also something I want to tell you. So I'm redrawing this example. And I have here processes which correspond to some measure Pn, which starts at 1 over n. And I mean, if you look at these processes, they should converge to something. I mean, also, if you look at these processes for different n, then those are a Cauchy sequence. And so if you are in a nice space, you should have a limit, yeah? So if you are in a complete space, these processes should converge something. And morally, what they converge to is a stochastic process which starts at 2 points which are on the same level, but these points still allow you to distinguish the information whether you're going to go up or down into the future. Okay, so what I'm trying to say here is that adapted Wasserstein distance for these processes is not complete. And actually all of these, with all of these topologies you can attach some metrics, and naturally they are not complete. And of course that's a bit bothering, and somehow you know what the object in the completion should be, but it will not be represented in this classical way. So for a while I thought this is sad, but by now I think it's actually something nice behind it. Namely, you can, if you want to go to the completion, what you end up with is precisely stochastic processes plus a filtration where the filtration is potentially non-trivial. Yeah, so if you think about back to stochastic processes, there is always this setup. You have a probability space and an adapted process with respect to some filtration. And I mean, if you are in this setup, you can again introduce this adapted Wasserstein distance. You look at couplings on the space, which in some way respect the filtration. And you need to make some identification when they have distance 0. Well, the reason is that if you introduce different probability spaces, you can have lots of nonsense in it. So you have lots of redundancy. To get rid of this, you want to identify this. And what you end up with is this turns out to be actually precisely the completion of just taking probability measures on Rn together with adapted Wasserstein distance. So stochastic processes with filtration is an object which is studied since the 1930s, and before working on this, I was never understanding why you have actually other filtrations than just the canonical filtration on a path space. And yeah, it turns out it pops up here. It is a way to represent the completion of probability measures on Rn with adapted Wasserstein distance. Yeah. So in this specific case, what would happen is that the filtration at this time 1 already knows something about the future. So this would be a natural way of representing this type of stochastic process. Okay, you also get a number of further properties you would like to have. You get that this is a geodesic space. Martingales are a nice class of processes, or my favorite class of processes, and they turn out to form a geodesically convex subspace. It's also isometric to a Wasserstein space in a classical sense. Easy processes are dense, so the topology is not too tight. You have a nice Prohorov result, meaning you can easily understand what compact sets are, and you can do things like barycenters on the space. So this is an example. This is some numerics which were done by Stefan Eckstein. The idea is here, these are 3 different models, like CRR type models you could use in finance, or you would use in finance. Maybe you think that different experts believe in different models, and a barycenter is now a way to reconcile these models. Yeah, so it's a, I think, appropriate barycenter in order to reconcile different viewpoints about how to model some phenomenon. What's also important with looking at this completion is that now you have a much better understanding of compact sets, and what Gudmund-Pammer noticed that understanding compact sets is maybe the real explanation about we end up seeing the same topology again and again. Yeah, so in topology, there is this fact that if you have 2 compact topologies which are comparable, then they already have to be the same. And I mean, there is a slight twist to this lemma. If you have 2 topologies which have the same pre-compact sets, then also they have to be the same. And in our setup, somehow this is the topology which looks the weakest, this is the topology which looks the strongest. There is still quite some work involved, but you can show that they have the same pre-compact sets. And from this, Gudmund-Pammer obtains that those topologies are actually the same. And I think it's really the explanation behind why we, with so many topology, with so many different metrics, we end up seeing the right topology in the end. What's also great, well, what I find very great, what I really like about his proof is that now you have a chance to do this in continuous time. So what we see is actually the same phenomenon works also in continuous time, also in a continuous time setting, where you can look at, where people have been looking at these different topologies. You end up seeing that they are the same. Once again, if you allow for non-trivial filtrations, you get a Polish space. So the space of all processes is a Polish space. It's a completion of stochastic processes which are on this Skorokhod space. Again, you get continuity of optimal stopping problems. Again, martingales are a closed subset. Processes which you get by discretizing are dense, so it's a not too fine topology. Classic theorem in probability is Donska's theorem about approximation of Brownian motion with random walk. It's also true with respect to this stronger adapted Wasserstein distance. Most but not all of the things we have in discrete time are equally true in continuous time. I want to make one remark, and namely that in continuous time, what seems to be important is to allow some flexibility with respect to the information structure. So here I have a notion of bi-adapted mappings plus some epsilon, and this epsilon is allowing you to look a bit into the future. So you're allowed to look into the future for an epsilon time step, and you pay an epsilon price for this. It turns out that this is the metric which will metrize all previously known topologies. If you don't put the epsilon, you get a new metric, and this metric is too fine in the sense that you do not obtain a separable space anymore, and you have no approximation by simple processes anymore. Yeah. My favorite open question in this field, in discrete time we had a geodesic distance. What would be the natural geodesic distance in continuous time? And of course there's many other open questions, but yeah, that's my favorite one. Thank you for your attention.
Thank you, Matthias. Do we have lots of time for questions? Yann.
So you discussed the uniqueness of the topology, but on the metric side, so do you have some special preferences for? I mean, you wrote one of them, right?
Yeah.
But is there some criteria that would favor one metric with respect to another one?
I mean, certainly at this workshop, no, we want to have adapted Wasserstein distance, yeah? I mean, you can, okay, so there is, so the topologies are the same, but these metrics are actually not equivalent.
Yeah.
Yeah.
So, yeah.
And the completions with respect to these metrics are also of different size.
Mm-hmm. Mm-hmm.
And this would mean that other topologies or metrics behind this would fail to distinguish stochastic processes which you should distinguish.
Mm-hmm.
So actually with respect, so with all other metrics we put here, what can happen is that two processes are the same. The matrix says they have distance 0, but actually optimal stopping problems are not the same. So they don't have the same probabilistic properties in a way. Also, I mean, Hoover-Kiesler, so they are logicians, and I mean, they have a very original viewpoint of theory of stochastic processes. Yeah, so they think they really discuss what are we doing as probabilists, what are operations of the probabilistic language, and their topology is make everything continuous which you can express in such a probabilistic language. And it's very reassuring that this Hoover-Kiesler metric is equivalent to adapted Wasserstein distance. So it means that adapted Wasserstein distance really allows you to distinguish all probabilistic properties, whereas the other metrics are not strong enough for this. And yeah, one exception to this is Knote-Rosenblatt is even stronger than adapted Wasserstein distance, but I think Knote-Rosenblatt is too strong. And I mean, the reason is that with this adapted Wasserstein distance, you have this Prohorov theorem. Prohorov tells you that as long as you're inside some compact domain, yeah, you're compact. It's something super useful, which we use all the time in probability, and this is something that is lost if you work with Knote-Rosenblatt. So for me, that's the reason. So most of the metrics are too weak, and Knote-Rosenblatt is too strong, and adapted Wasserstein distance is my favorite. Yeah.
This was exactly a question of this kind, right? So they are Knote-Rosenblatt and adapted distance you showed us are topologically equivalent, but not metrically. So can you say more, or at least at a local level, can you compare metrically the balls for the two metrics? Do you have comparisons?
No. I mean, Knote-Rosenblatt, so, I mean, if you have two processes, so if you have this process and that process, I mean, for adapted Wasserstein distance, those two are very close, yeah? And also, I think morally, those two are close in a sense that the position of the points is always very similar, and the information you get at this time point is also very similar for these processes. So those should be close, but then if you do Knote-Rosenblatt, then you couple this guy with that guy, and of course that's a very bad choice because this path is going to be coupled with that path, and yeah.
And may I ask another question? So you showed us some examples of barycenters. Can you say a little bit more about the numerics for performing this?
Yeah, so this is Stefan Eckstein. Okay, yeah, Stefan Eckstein is also a postdoc in Zurich. I think he's great for all of these things. I mean, adapted Wasserstein distance is often numerically easy because you have some DPPs, the dynamic programming principles, so you can calculate them from back to front. Yeah. I think Stefan and Gudmund Pammer have something about Sinkhorn for adapted Wasserstein distance, but it turns out that Sinkhorn is maybe not much better than doing it from back to front. Yeah. Here it's canonical filtrations. Yeah. But I mean, it's so if you don't look at non-trivial filtrations, then your space will not be convex. So you will have holes. You can have two processes with canonical filtrations, and their midpoint is having a non-trivial filtration.
The question was, what are the filtrations?
Thank you. So always about if you want distance and the barycenter, because you said in the last slide that you don't know about geodesics, right? In the continuous time.
Yeah.
But so does it mean that actually AW is geodesic or not? So it's length or it's not.
It's not length.
Okay. But in the discrete case, you can characterize.
In the discrete case, it is length. In the continuous time case, it's not length. And I mean, what's going on is that in the discrete case, I mean, times are really distinct. There is no way to shift back and forth. And in continuous time, you're allowed to shift information as well. I mean, I don't know. I guess the moral in the idea in continuous time is, if you have a process which is just this path, and then you have another process where the information is just slightly shifted, you want these to be close, yeah?
So you don't have the convergence, plain convergence of discrete time to continuous, but you have to allow also time steps that are moving.
Yes.
Okay.
And if you don't allow it, then you lose separability. And I mean, Donska is saying random walk is close to Brownian motion if you properly scale it. I think you really want to have Donska for a good topology here. And I mean, if you want to have something like Donska, you have to, you have to allow to spread information a bit. Yeah.
Okay, other questions? So if not, we can thank the speaker once more and adjourn to tea. We resume at 11 a.m. Okay, so let's see, before we have our final talk of the day, I would like to acknowledge first of all, the wonderful support that we've received by the SNS and Centro de Giorgi. So Laura, Antonella, Federica, Luisa, who's not here today, thanks to the staff. And thanks also to Giuseppe, Luigi, Nicolo, and the other Giuseppe, who also isn't here today, for organizing such a wonderful conference. Thanks for having us here in Pisa. And finally, our final speaker today is one of the leaders of the Renaissance of optimal transportation. He needs no introduction, Yann Brenier, and he's going to tell us about common variational principles for Euler, Einstein, Schroedinger equations in the quadratic optimal transportation style.
Okay, thank you, Robert. Well, I cannot say again that, of course, we are all grateful to the organizer and to the De Giorgi Center for this wonderful week. Okay, and so today I would like to discuss the possible generalization of the quadratic optimal transport problem written in Eulerian coordinates, or what the people call the Benhamou-Brenier type formulation. And the goal of this talk is to show that actually you find so this, let me just to refresh your memory, or if you didn't attend the first part of this week. So I just remind you this formula that if you are given two density rho 0 and rho 1, you look for a kind of fluid of density rho and velocity v, which is interpolating between the rho 0 at time 0 and rho at time 1, and subject to the continuity equation. And you minimize the time integral of the kinetic energy of this fluid. So it's a very elementary idea, but it turns out that it's absolutely equivalent to this, to the Monge distance of order 2, the quadratic Monge distance or Monge-Kantorovich distance between rho 0 and rho 1. And the optimality equation is also very well known, at least at the formal level, because there are some technical difficulty depending on the data. So essentially, the optimal velocity is potential. So it's a gradient of something. So it's curl-free, no vorticity. And on top of that, you have the Hamilton-Jacobi equation, which is also known in fluid mechanics as the Bernoulli equation, but without pressure. And so we get the model of pressureless Euler. So in some sense, you can see that at least in the quadratic case, the Monge problem can be seen as a subset of the richer theory of Euler, which was designed a little bit before in the 1750. Also, Monge introduced this optimal transport problem in 1780. Okay. So in some sense, you see that in this talk, Euler is already present at the very beginning. Okay, so now the claim of the talk is, as I said, we can build up some generalization of this problem, and I claim that this contains important equation of mathematical physics. So, for instance, the free Schroedinger equation, and something that looks completely different, which is at least the Einstein equation in vacuum. So, in some sense, I try to put in the same framework equation of mathematical physics which are poorly related, because Euler is super classical, Galilean invariant. You know, Schroedinger is quantum. It's not compatible with relativity. And of course, Einstein is fully relativistic, as we know. So, I mean, how can they be put in the same framework? So the drawback of this approach is purely formal. So what I'm going to do in this talk, there is a strictly zero level. The level of analysis is zero. So it's just calculus. I'm just playing with equations. And the big loss will be convexity. So as I said in the first slides, we know that maybe I can go back for a second into the first slide. So we know that this problem is convex once you take the good variable, so rho and the momentum rho v. So it's a convex problem, and in what I'm going to tell, actually, the convexity will be heavily lost. And therefore, it is really hard to know at the moment whether these ideas can be used fruitfully at the analytic level. So maybe there is not much to do with this. But anyway, I hope this will be at least entertaining. Okay, so then, and actually we can do a little bit better, which is, in my opinion, even more convincing. So for instance, we can include the Euler equation with a genuine pressure, and in particular the case of isothermal Euler, where the pressure is linear with respect to the density, and for the Bernoulli law, it means that you have a log, and the c is not the speed of light; it's the speed of sound, and in this model, the speed of sound is constant. So it's a gas with it has a constant speed of sound. Okay, and you can do something really looking the same at the algebraic level, I would say, if you add the cosmological constant to the Einstein equation, so which means that the Ricci of the metric is proportional to the metric itself, with a constant, which is a so-called cosmological constant. So according to the physicists, the lambda is a tiny positive constant. So this corresponds to a kind of, in the Euler framework, to an imaginary speed of sound. But you shouldn't be too offended by that, because in optimal transportation and mean field game theory, people do that all the time, because they have typically this congestion problem are the time boundary in the future and in the past, and they cannot be compatible with the real speed of sound. So this is typically the imaginary speed of sound. So there is nothing so wrong about considering a negative minus c square, but I keep the notation c in just in order to keep track of fluid mechanics. And in the case of Schroedinger, linear Schroedinger, the good thing is by doing this, you can add nonlinearity to the Schroedinger equation, so you can really address a nonlinear Schroedinger equation, and what corresponds to the isothermal gas for Schroedinger is not the usual cubic Schroedinger, it's a logarithmic Schroedinger equation when you multiply the wave function by the logarithm of the length of the wave function. It looks like a curiosity, but this is attracting more and more attention. There are recent papers by people like Rémi Carle in particular, Rémi Carle is French, and Isabelle Gallagher and other people, because this equation has some deep link with the heat equation, and there are some very interesting results on this equation, which are very different from the usual cubic Schrödinger equation, for instance. So this is the program in some sense. Okay, but in order to not make things too complicated, I will just concentrate on the case where there is no C and no lambda. So which means that in the Euler case, we go back to the pressureless Euler equation. And in some sense, the standard optimal transportation problem has done the job. So there is no need to go back to Euler now, since I removed the C. Okay, otherwise I would have to work a little bit more. Okay, so now let me mention that, of course, there's been, actually, if you were here yesterday, it was absolutely obvious that there is a big link now between optimal transport and general relativity. And, of course, our chairman has been one of the contributors, and it's pretty recent, actually. And, of course, Andrea Mondino and Fabio Cavalletti talked about that yesterday. But as far as I know, all these approaches are based on this Sturm Lott-Villani synthetic formulation of the Ricci curvature. And what I'm going to talk about is, in some sense, is more elementary. I don't think it's related, but maybe wrong. And as I said, what I'm going to say is purely formal. It's just pure computation, no analysis, no estimates, no functional space. Sorry about that. But this is the final talk, so we can make a little bit lighter the discussion. So let me start by some appetizer or antipasti, as it should be said in Italy. So but because it's not so known. So my first example is not related to mathematical physics, but, well, I mean, not to standard mathematical physics, but rather to random matrices, because we can look at this Eulerian optimal transportation problem in the complex framework. So, for instance, we are looking, and let me do that in one space dimension. So we have what was denoted by rho, and let me denote for some reason by C now. And so we have the density field C is complex valued, and the velocity field V is complex valued, and we are talking about the real part of CV square. So this is complex square. It's not length of V squared. It's really the square. And the continuity equation is the same. So this is complex, and CV is a complex product. So it is quite easy. I mean, you should do that as a test to see that when you look at the formal optimality condition, you get the complex Hamilton-Jacobi equation, or if you prefer, in terms of the derivative of the potential, so which is V, so you get the complex Burgers equation. So it's a Burgers equation with a complex variable, and you may know that complex Burgers is very different from real Burgers, because complex Burger is much more like Cauchy-Riemann. So it's more like a space-time elliptic equation, although Burgers is a prototype of hyperbolic equation. So this is the fact that you pass from the real to the complex numbers. And then, therefore, you already in this example, we have this pattern of something which is not convex a priori, because CV square is pretty bad. I mean, you don't see any kind of convexity like that. However, there is a very easy, actually, transform that makes this problem convex. So I didn't tell you exactly the transform. So this was already seen a long time ago by Alice Guillonnet 20 years ago in a paper. And actually, the idea came from somebody from the Soviet school, actually. And then it boils down to, maybe it's very small here, it is a little bit like the related to actually to the Euler equation with a pressure which is cubic, but with an imaginary speed of sound, because you have a plus here. So for Euler, you should have a minus, and this would be a critical point. So it will be like a saddle point. But if you put a plus and you assume rho to be non-negative, this becomes a convex minimization problem. And this is good enough to address this equation. Yeah, I don't exactly remember the connection between W, but W and rho are real here. Yeah, definitely. And so in some sense, this is good news, because even if you have a formulation which doesn't look at all convex, then there is some hidden convexity, at least in that case. Of course, I doubt it's true for the more complicated model that I'm going to discuss now. But anyway, it's not so bad, actually. So maybe there is some possibility to do something. Okay, so now let me move to the rather simple example, which is the free Schroedinger equation. And there is a formulation which, as far as I know, it's not known, or it's certainly not popular. It's the following principle. So once again, I don't take care of boundary condition. I am just playing the game of the least action principle just to derive equation as people would have done in the 18th or 19th century. Just a trick to get equation, nothing more. So here we are looking for fields which are vector valued, but we are in a higher dimension D, and V is a vector of complex numbers, so it's in C to the D. And what we are looking at are critical points of the integral of the sum from K1 to D of the real part of CVK square. Once again, this is the complex square. Don't put any norm in that business. And then we have the continuity equation, and here there is something new. And so this is really the quantum part of Schrödinger. So you have to add this dispersive terms to the continuity equation. So let me just make a comment. Adding something to the continuity equation is very popular in the field of the Schrödinger problem, which has been discussed a lot this week also. And usually you put the heat equation. You have the heat operator, but here we are not in the world of the Schrödinger problem, but in the world of the Schrödinger equation. And there is a definite change of sign. And therefore, we have to switch to complex numbers. And here, what substitute for the heat operator is this dispersive operator, which is of very different nature. It's a dispersive equation. And you have this principle. So you can say, okay, this is ridiculous because the Schrodinger equation is linear, and in the constraint, you see that the linear part of the constraint is already the Schrodinger equation. So it looks like putting the Schrodinger equation in an artificially complex, difficult framework. It's completely ridiculous. However, you can do the same trick for the logarithmic Schrodinger equation, so which is nonlinear. So then it makes more sense to do it. Okay, and at the end of the talk, if I have enough time, I will tell you how you can get this formulation. It's very simple to do, and it might be more or less known or classical. I didn't check carefully. It's more like an example for me. Okay. Now the main interest for me was really to deal with Einstein equation. So let me just draw first abstractly the generalization of the quadratic optimal transport problem I want to discuss now. So I am putting myself on the space R8. So now instead of the time and space as I had before, now the first variable x is in the space-time variable in R4. And the second variable xi is a tangent vector. So it's a tangent bundle of the space-time, if you want. Xi. So this is R8. And now I am looking for fields, C and V, and this time they are not real number or complex number, they are 4x4 matrices. So of course you remember that complex numbers are just spatial 2x2 matrices. So here, real matrices. So here I jump to 4x4 real matrices. And I can compute, of course, the product of these two matrices, C, V square, and I take the trace. Once again, this is not VV transpose. This is just CV square. So I'm totally respectful of the square. Okay? And the new continuity equation looks like that. So you see the big difference is that you have, instead of the time, you have a multi-dimensional time in some sense now, and here you have the tangent variable. Okay, so that looks like a big change, and there are some additional constraints. So which are, but they are minor constraints because they are linear. And for instance, it's written in small letters. So for instance, the first one just tells you that we ask V to have a potential with respect to the xi variable. But you remember that we already have that in the optimal transportation problem in the sense that the vector field is potential. So in some sense, it's the same thing. So here, V has a potential in xi. C used to be a real number. And therefore, you have also a similar condition for C, which is a little bit more complicated because you have to play a little bit with the diagonal. Okay? Anyway, and this is new with respect to the previous framework. Because before C was a scalar, so there was no point to do that. Okay. What else? I wanted. Yeah. So maybe you could say, well, it's really very different to use a multidimensional time. However, I didn't put a transparency on that. You may know that there have been some very interesting work a few years ago by Hugo Lavenant on the generalized harmonic maps or soft maps. Where which amounts to do the classical quadratic optimal transport problem, but with a multidimensional time. So there is nothing wrong so far of using a multidimensional time in this framework. Okay. If you want, I could explain to you later if you are interested. So, but there is a connection with the work of Hugo.
But in the classical problem, you don't need to impose the symmetry constraint. It comes out of the optimization.
That's true.
That's not the case.
That's really a good point because in the analysis, this plays a role. This constraint plays a role. So in this sense, there is a difference. Yes, because if I ignore these constraints, I didn't check very carefully, but I don't think it comes automatically from the optimality equations. No, I'm pretty sure it doesn't. Okay, that's excellent point. Yeah. Now, so let me tell you the only result of this talk. and once again, it's not a result in analysis, it's just a computation. So let me tell you what is the result. So you take a Lorentzian metric, G, you assume that it's smooth enough to justify the calculation, and I denote, as usual, the Christoffel symbol by gamma. So if you are completely afraid by Christoffel symbol is just kind of logarithmic derivative of the metric. Okay, it's a fancy, slightly complicated formula, but it's essentially some derivative of G multiplied by the inverse of G. Okay, and then what you introduce, this field of matrices, VJK, so the indices G, K, Q range from 0 to 3. It's 4 dimension, and 0 is the usual notation for time in the general relativity. So, so the definition of VJK is very simple. You just apply the Christoffel symbol, which has 3 indices, to a typical tangent vector psi. And this makes a function of x and psi. So it's a little bit funny because it looks weird to consider a general function of x and psi, although in the concrete application, you just take a linear one. Okay, and I could comment on that if you want later on. Okay, and now for C, it's slightly more complicated. C has a potential, but as I told you, there is something to do with the diagonal, so it's a but you can just think about C deriving from a potential with respect to the variable psi, and there is this correction. And now the funny thing that there is a closed formula for A, which is built on the metric itself and not on the Christoffel symbol. So you have a clear separation between the Christoffel symbol for V and the metric for C through A. And there is the determinant of G. It's not the square root of it, it's a determinant. And there is the cosine of the quadratic form associated to the metric, acting on the tangent vector. And you have the cosine. So this looks like a Gaussian in psi with the weight given by G. However, in this framework, because of the signature of the, I mean, you cannot integrate the exponential, the real exponential. So you have to make the exponential imaginary. And as we know from our master Leonhard Euler, that the real part of the imaginary exponential is a cosine, which is a contribution of Leonhard Euler, actually. So then I claim that with this formula, CV is a critical point of the problem I just wrote. Okay? And since, yeah, for the oldest people, maybe I just put against the, if they forgot already. So the problem I just wrote before. So in some sense, the critical point of this problem contains as the solution of the Einstein equation has very special solutions, because in the Einstein business, the V is linear in psi. So this is like a huge embedding of the Einstein equation in something much bigger, and the drawback of that, it's not so clear that it's tractable. Anyway, the structure, you see, the structure is not only looking like optimal transport, but it's looking like quadratic optimal transport. So this is a super conservative hardcore of optimal transport. Okay? No square root, nothing like that. Okay, so I don't know how much. Fantastic! There is a clock.
It's about 5 minutes left.
Late, you mean?
Yeah, you have about 20 minutes.
Okay, fantastic. But I really appreciate that there is a clock. Yeah, that's getting rare now. Okay, so the one part of the I will not talk so much about the proof in the case of the Einstein equation because it's a bit messy. So I will do that for the Schrödinger equation. However, I would like to tell you an important information from my viewpoint on the Einstein equation, that by using this trick, first of all, there is something I'm not a geometer, but I was very glad to see that using this variable, it's much nicer to read the Riemann tensor. So for instance, I know by heart the Riemann tensor by this trick. So the Riemann tensor, so if you consider this field of matrices as a collection of 4 vector fields, so the vector fields with indices j, but the label of the vector field is given by the lower case k. So you have 4 vector fields, indices with index k, and then you see that the Riemann tensor in this phrasing looks like a commutator between the field Vj and Vk. So it's very easy to remember. Now, up to the sign. So the only thing I cannot remember is what is a sign. But otherwise, I know I can do the Riemann curvature very quickly like this. So it's a good trick. I don't know if geometers or general relativity people would acknowledge that, but it's very easy to remember this way. Okay, sorry.
It also looks like an advection operator.
Yes. Yeah. Yeah, this is what I mean by commutator. So like the advection is exactly, you advect Vj or by Vk minus. Okay. That's right. It is exactly the way I am thinking of. Okay, and then there is an additional nice structure because you see it's not in conservation form. And I belong to I was educated in the field of conservation laws. So I like that. And it turns out that you can write that in conservative form. You can put the derivative outside of the nonlinearity. Why is it so? Because you have to use a non-trivial property of the Christoffel symbol is the fact that the Christoffel symbol in general relativity is symmetric in the lower indices k and gamma, which means, geometrically speaking, it means that the connection is torsion-free. Okay, in my opinion, this should be more or less in the phrasing of fluid mechanics like to being vortex-free. So I think probably torsion and vortices, it's not so surprising that torsion and vortices must be related. Okay, so you get this formula, and of course, to get the Ricci curvature, you just collapse the index n and m, and you get immediately the formula for Ricci. Ricci is much harder to remember because the contraction of n and m makes the formula obscure. So if you really, in my opinion, in my test, I don't remember the formula for the Ricci curvature, but I do remember it for the Riemann tensor, and then I just collapse it after. So it's like a lifting of the Ricci curvature. Okay, so now you see that writing that the Einstein equation in vacuum is just telling you that the Ricci curvature of the Lorentzian metric is 0. Okay, and therefore I just tell you that this you get this equation, and you see that this equation looks like a Burgers equation. So you know, if you think that x stands for the time, so you have a time derivative of v plus the space derivative of square of v. So it's just kind of matrix value generalization of Burgers. A weird one because there is some kind of twist in this formula, but looks like Burgers equation. So yes, but I think the signs are correct.
No, but this is different from the Burgers equation.
Oh yeah, that's right. Sure, yeah, I agree. Yeah, so it's not exactly sure. So it's one possible generalization of Burgers equation in this sense. Okay, so of course, maybe if you are really careful, you see that something is missing because an important information is that the connection should be the Levi-Civita connection associated to the metric. So there is some need to say something about the metric. But we will see, actually, this comes up automatically through the method I'm going to explain in the simpler situation of the Schrödinger equation. And okay, so this comment is a little bit mysterious, so just forget this if you are misled. So
there's also the question of lifting the metric from the manifold to the tangent bundle, I guess.
Yeah, okay. This is local theory, so you don't care about the topology. Are you worrying about the topology of?
It lifts automatically to the cotangent bundle, but then if you want to do the tangent bundle, you need to make a selection. There's a standard way to do this.
Ah, yeah, okay. I see what you mean. Because this is really the tangent bundle. It's not the cotangent bundle. Yeah. Yeah, okay. So there are a lot of discussion about how this fits with covariance requirements. Okay, this is not very clear to me. So, but anyway, let me continue. So now let me move in the minutes I am left with to the treatment of the Schrödinger equation because it's more or less very similar ideas. So the first step, which is specific to Schrödinger equation, is to use something which is essentially the Madlung transform, but it's not written exactly in the way of Madlung. So you, but this is also the usual trick for the heat equation when you write the non-negative solution of the heat equation as an exponential, and you get the viscous Hamilton-Jacobi equation, which plays such an important role in probability, and I mean it's a prototype of large deviation theory, blah blah blah, and the connection between probability and optimal transport. Okay, so but of course at the level of the Schrödinger equation you have a dispersive equation, so you cannot expect to have anything like the heat equation, and you get this kind of dispersive complex Burgers equation. Of course, I had scaled the Planck constant to something, maybe in order to not complicate the formula. So you get this equation. So just first step. So you start with a very simple linear equation, and you make it more complicated by doing that. But we know that for the heat equation, it's a very good idea, actually. So it's strange, actually. It's this kind of a complex version of the Hopf transform. Okay, so nothing new at this level. So now, since I am not very comfortable with complex number, let me just write and I'm going to work with the gradient of phi, and I will separate the real part, which I denote by W, and the imaginary part that I denote by G. And then, if I didn't make mistakes, you recognize in this equation the system coupling W and G through this. You recognize the square here, the complex square here, and then you have the dispersive term that you write like the divergence, the gradient of the divergence of G. This is the right way to write it. So this is substituting for the expressing the Laplacian of phi. So in some sense, you take the gradient of this equation, because this is like a Hamilton. Actually, maybe I should have said, sorry, this is maybe a typo. This is Hamilton-Jacobi, okay? Because you have the square here. So sorry, I should have said the dispersive complex Hamilton-Jacobi equation. And here I do the usual trick of taking the gradient, and I get the complex dispersive Burgers equation, sorry. So I should have put here, you should read the Hamilton-Jacobi. Okay, that's the first step. And then the nice thing about this structure is you see that it's also of Burgers type, in the sense that you have a linear part involving the time derivative and the quadratic part involving the space derivative. And this structure is common to all those models I discussed, including the one where you have a speed of sound for isothermal Euler, the cosmological constant for Einstein. So you always have this quadratic structure. Oh, well, I mean, this would correspond if you had the logarithmic for nonlinear logarithmic Schrödinger equation, you would have to add some additional term. Yeah, but there will be linear. So in some sense, the fact that I concentrate on isothermal Euler and logarithmic nonlinear Schrödinger is then I get a more special structure, which I also get in the Einstein equation with the cosmological constant. So in some sense, the Einstein equation with the cosmological constant correspond to two special situations in the Schrödinger world and in the Euler world. Okay? So of course you could play with generalization to more general pressure law, so I don't know if it has any interest. Yeah. See, if, for instance, if the cosmological constant is not constant, actually, so it's okay. Maybe I'm sure there are some exotic theory of that style, but I don't want to enter this. Okay, so and now, so actually it's pretty trivial trick, but it's quite interesting to do, in my opinion. So the idea is you write this equation in weak form. So you have test function. So I collapse the two weak formulation in one cell. So for the equation involving dtw, I multiply by a. So w is a vector, is a real vector. So now there is no complex notation anymore. And then therefore, in order to write the weak formulation, maybe let me go back here. So here, this is a vector valued equation. So w is a vector in Rd. And you have to multiply this by a test function a, which is itself valued in Rd. Okay? And I do the scalar product, I integrate by part. And b, exactly. Yeah, absolutely. So scalar product of this by a real scalar product with some test function, real valued, a vector valued, the real vector valued function a and b for the second one. And what I get is this thing. So this, you recognize the integration by parts, dtw, the gradient of v square minus z square. And here, okay, this is funny formula for the gradient of the divergence, which is in some sense symmetric. And now, but what is not so common is to consider this integral as Lagrangian itself. Because usually, the weak formulation, you just say that this number is 0 for all test functions. But in my opinion, it's much more interesting to consider this functional as a Lagrangian, okay, involving the test function a and b and the original variable w and g. And this kind of trick, I used that some years ago in to address evolution equation like the incompressible Euler equation. And Dmitry Oborotnikov from Coimbra has developed that in a much more, a lot in the spirit of quadratic equation. So there is a nice, I don't think it's yet published, but there is a nice preprint of Borotnikov on that. And the same trick can be used for all equations I define. So including log Schroedinger and vacuum Einstein with cosmological constant. Okay, so now this is the first step is, of course, if you differentiate this Lagrangian with respect to A and B, well, it's pretty trivial because A and B, you just get the original equation. This is the purpose of the weak formulation. You can say the weak formulation is just what you get by differentiating with respect to the Lagrange multiplier. So this is what we got. But of course, we get this kind of adjoint equation if we are using the phrasing of control theory. So you get this adjoint equation by derivating in W and G. And of course, this should be linear because the Lagrangian is linear in the test function. So we get linear equation in AB with coefficient depending on W. So you have a kind of triangular structure where you have the original equation which are autonomous. They don't care about A and B. And the Lagrange multiplier are just slave by them and they are just following a kind of non-constant coefficient linear equation. So that's the structure. Of course, when you input C and lambda, it's slightly more complicated. Yeah. Okay, so now the trick, which in my opinion is the same trick. Actually, I didn't try to work out that so much, but it's essentially the same trick when you go from the Lagrangian to the Hamiltonian in classical mechanics. So here it amounts just, this is the following trick. So you take you eliminate in the Lagrangian the time derivative by using this this adjoint equation. You just substitute. It's kind of funny game because most of the terms cancel out because of linearity, and you get a new Lagrangian that I call L sub 2, where you have done this substitution, which is substantially simpler than the previous one, as you can see. But the penalty for using this reduced Lagrangian, L2, is that now I have to keep this equation are constraints. So the Lagrangian before was without any constraint. Now I consider L sub 2 subject to this equation 2. And that's interesting because, as we are going to see, in the simplest situation of the classical optimal transport theory, we would start from the Hamilton-Jacobi equation, for the Burgers equation. You would do the same thing, and out of that, the continuity equation will pop out. So in some sense, as I used to say in previous talks, this is like you are very ignorant, or you are in a different planet, so you have never heard about the density field, the continuity equation, the kinetic energy. You just know the Hamilton-Jacobi equation. This is the only thing you know. But by this trick, you can recover the continuity equation, the density, and the kinetic energy. So it's nice. And then I do that in a more complicated situation of the Schroedinger equation, but you already see the structure appearing, because you know it's very now tempting to give a name to this divergence of A, like a kind of density field. And this is what I'm going to do in the next slide. Okay, so it's very tempting to introduce. So I don't use the letter rho on purpose. So I use R instead. So it's the divergence of A, and there is a kind of additional field S, which is the divergence of B. And if we apply the divergence operator to the previous equation I wrote, this equation 2, this constraint, you see that the divergence of A and divergence of B are everywhere. So in order to get a self-consistent equation for divergence of A, it's just enough to put the divergence operator in front of that. And then this is what I do, and I get this equation. So you see that looks like a generalization of the continuity equation, because if S was 0, for instance, the first equation would be just the continuity equation for some kind of artificial density field rho advected by W. But here it's more complicated, because there is a coupling between all these quantity, and the updated Lagrangian now looks very much like optimal transport style, especially if S and G are 0. You really recognize our old-fashioned optimal transportation. And here this is a real square. This is the length, the Euclidean length of the vector. So it's not there is no complex number anymore here. So this is what you get, and of course you get the new term, which is the minus G square, and this product of W and G. So if you compare with the classical optimal transportation problem, you see that it's richer, because you have this additional term, and also there is this dispersive term. Okay. And you see, this is not the Laplacian, the Laplacian of S is acting on R, and the Laplacian of R is acting on S. So it's not the heat equation. So it's a Schrödinger equation. Yeah, but it's really dispersive. So it's not, because you see the sign are not the same. So it's really, I mean, okay, so now I claim that in some sense I have a possible, because at this point it's just a guess, a possible formulation for the Schrödinger equation, and you can check that you can recover the Schrödinger equation this way. So you work out this variational principle, and then you will get back to the Schrödinger equation. Okay, and of course in complex notation, if I am restoring complex notation by using C to be R plus IS and W and V to be W minus IJ, I recover exactly the variational principle I started with some slides ago. Okay, and of course the same technique works for Euler, so it's very easy to do it for Euler. For Einstein, it's a little bit more subtle to do it, actually. There are some complications, but it's essentially the same technique. And yeah, and I think that's the end. And I'm repeating what Robert said very nicely at the beginning of my talk, that thank you very much.
Questions for Yann?
Oh. So in this case, for example, so what is if there is any intuition for the velocity Vk? So
well, you mean the interpretation? Yeah. Yeah, actually, VK can be VK can be related to you can interpret in terms of the solution of the Schrödinger equation. But I think a better answer to your question is just to look at the other example of the Einstein equation. So if you do this the same thing, that you will end up this with this formula. So in some sense, the V you will be interpreted nicely in the equation you are treating. So what is more, actually, this suggests something really interesting in my opinion, because in some sense the difficulty is not V, is C. Yeah, actually, let me rephrase your question. So in some sense, your question is really excellent in terms of what is the interpretation of C. Okay, so for Schrödinger and Euler, it's pretty obvious. However, for Einstein, it's much more mysterious, and you see that C is related to the metric in a rather, I think the formula is very pretty, but it's quite involved, because in order to interpret C, you have to go through this potential, which depends on the metric in a rather complicated way. And I didn't write the formula, but there is an inverse formula. You can recover the metric out of A also. That I must maybe I can. So the formula is like this: the determinant of G times the inverse metric Gij is just given by the integral of xi. Yeah, that's right. Xi I aj minus xi j ai and dxi. So it's a function. Of course, this should be a function of x only. This doesn't see the tangent variable. So you integrate with respect to xi, and you remember that in the definition of A, this is like a Gaussian. So it's a Gaussian integral. It's an imaginary Gaussian integral in xi. And actually, if you work out the integral of CV square, you see that it's just an expansion of the Hilbert-Einstein Lagrangian written as a Gaussian integral. So I don't know if it's a known trick, but you know the Hilbert-Einstein looks like that. So you have the square root of the minus. I mean, there is here there is a minus. Yeah, or that G. So I put the signature -1. Yeah. And you get the Gij Rij dx. But actually, this is really a Gaussian integral, and it turns out this is the same as CV square with this formula. Okay, but I don't.
It's a Gaussian integral on tangent.
Yes, and it must be known. I mean, this is so clear, obvious. Well, I mean, but I don't know. I didn't see. Okay, if you. Okay, the expert. I mean, you are the only expert left, I think. Okay, sorry for the other people. Maybe you are expert also. So I'm not sure. It doesn't look standard. Maybe it's known, but it's probably not. It must have been denoted by somebody, right?
So actually, that last month in Toronto, we had a conference on non-smooth relativity, and the comment of Shadi Tavilda-Zadeh was that what's missing from this non-smooth approach to the relativity is the Einstein-Hilbert action. So now,
okay, very good. Yeah, but also another. Okay, no, maybe I should not make comments. So I should say answer questions.
Other questions? Well, let's see. I can ask you the question. What was the comment you were going to make?
No, because the funny thing I made. In some sense, you can see maybe in fluid mechanics, sometimes people consider, especially in geophysical fluid mechanics, people consider what is called zonal flows. And zonal flows are essentially when the velocity field is linear in x. And therefore, of course, you can do the entire theory of the Euler equation with zonal flow. So, and therefore, you will get some kind of matrix-valued problems with time-dependent matrices. And then it would have been funny if Euler had not discovered the Euler equation and if people had started with the zonal flow equation. And so in some sense, it seems to me that in some sense, like the Einstein equation looks like the zonal flow solution for this Lagrangian.
Because it's linear and
yeah.
Yeah, I see.
But I don't know. It's kind of just a provocative joke.
Any other questions for Yann? Okay, so I guess it's time to close the session. So maybe Giuseppe wants to say something still.
So first, thanks to. Okay, the workshop is over, and let me say that we, the organizers, are very happy of the quality of talks and of the number of participants, especially for young people. And this was possible thanks to all of you. First, the speakers. Some of them did a very long trip to come, and all the participants. So finally, but last but not least, special thanks to the secretaries that solve many small problems that occurred during the workshop very efficiently and always smiling. So thanks.